Hello students and welcome to a new lecture. In this lecture we will be learning about the different phase changes. So when we look at the changes, for example, when we go from gas to liquid, this process is known as condensation. But when we go from liquid to gas, then that is the evaporation or vaporization. When we go from gas to solid or solid to gas, solid is the greatest order when things are so close to each other, and gas where things are so scattered and far away from each other, so this is the least order. Let's talk about evaporation or vaporization. Liquids are constantly evaporating even when the temperature is less than the boiling point. And you know that if you put a cup of water and you leave it for days, it will evaporate eventually, even though it's not close to be at the boiling point. And that's because the molecule at the surface, at one point, they're going to get enough kinetic energy that they can break away from the intermolecular forces that's holding them to the other molecules on the surface. And the higher the temperature is, the more of them that will have the sufficient amount to escape. So if you look at this diagram here, this is the kinetic energy, and this is the amount of the kinetic energy on the x-axis that is needed to escape. Under the red curve, which is higher temperature, you can see that will be more fraction of the molecule have enough energy to escape the surface and become a gas above the surface, while the yellow area is how much or how many molecules at lower temperature will have that amount of energy needed to escape the surface. So it's natural that at higher temperature more of them will have that amount of energy to escape the surface, and then they become what we gas above the liquid, causing what we call vapor pressure. Vapor pressure has to do or directly related to the intermolecular forces. So if the forces holding molecules is weak, then they can escape much faster with lower energy. So here is a diagram to explain that. In order for a vapor pressure for certain molecules to reach, let's say 760, which is this line right here, if it's diethyl ether, I just need to heat for 34.6 degrees Celsius. If it's ethanol, alcohol, I only need to heat for 78.3 degrees Celsius, but if it's water, it's 100 degrees Celsius. And if it is ethylene glycol, it's going to be a very high temperature that is out actually of the scale of this graph. Why is this the case? This is here, it doesn't take much energy to heat the ether because those intermolecular forces are only dipole-dipole and they are weak. For ethanol, we start to have some hydrogen bonding, but it's not as strong as the hydrogen bonding in water, so that's less energy than water, and so on. Now, the volatile liquid, if you put one point at the x-axis, the temperature, then these are the liquids that easily form gas due to the weak intermolecular forces. So what you see here, that at 80 degree Celsius, or it's probably close to 78 degrees Celsius, you will see that let's point them here in color. This is ethylene glycol, this is water, and this is alcohol. Okay, and you see ethylene glycol has very, very small vapor pressure. Water at 80 degrees Celsius has like somewhere in the 300, while alcohol, which boils, is going to have the vapor pressure equal to the atmospheric pressure, and that's why it boils at this temperature. So those who have strong intermolecular forces will have a very low vapor pressure. Why? If there are strong intermolecular forces, they're not going to escape. And if they are not going to escape, they're not going to cause vapor pressure. But if many of them can escape, that will be high vapor pressure. And why when many of them will escape? Because those intermolecular forces between them are weak, so they are not held closely to the liquid. Okay, so now, does liquid hydrogen fluoride or liquid hydrogen chloride have a high vapor pressure? Again, we are trying to make an association between vapor pressure and intermolecular forces. Hydrogen fluoride, polar molecule, also hydrogen bonding. Hydrogen chloride is polar molecule, just dipole-dipole. This is hydrogen bonding and dipole-dipole. That's a very strong intermolecular forces. They will hold them each other very strongly, so very few of them will evaporate, meaning low vapor pressure. Okay. Arrange the following nonpolar compounds in order of increasing vapor pressure. Again, all of these nonpolar compounds will have only London dispersion forces. The only difference that with higher molar mass, it will be stronger intermolecular forces. So if this is the strongest intermolecular forces, that will be the lowest vapor pressure. And the weakest intermolecular forces, that will be the highest vapor pressure. All right, now let's define boiling. Boiling point is the temperature at which the equilibrium between vapor pressure of a liquid is equal to the external pressure, okay? So things boil when the vapor pressure starts to equal to the outside pressure, which is the atmospheric pressure. Water reaches that point, the 760, water reached the 760 at 100. That's why water will boil at 100. While ethyl alcohol reached it at 78.3. That's why it boils at 78.3. And diethyl ether reaches it at 34.6 and it boils at 34.6 degrees Celsius. Normal point, so when you see the word normal, pay attention that we are specifying that the pressure is 1 atmosphere. So this is the temperature at which the liquid boils when the external pressure is 1 atmosphere. So in a normal, I am defining the pressure, the outside pressure, the atmospheric pressure to equal to 1 atmosphere. Okay, so as you can see here, the stronger the intermolecular force, the higher the boiling point, right? And these are all nonpolar molecules, so it's going to depend on London dispersion forces, which depend on the molar mass, more dispersion forces, and higher boiling point. The molar heat of vaporization, that's another measurement that also judge the strength of intermolecular forces, is the energy required to vaporize 1 mole of a liquid. So if I have 1 mole of water and I want to vaporize it, how much energy should I give? That amount of energy is what I call heat of vaporization or molar heat of vaporization. Definitely a reflection of intermolecular forces. All right, which substance will have the larger boiling point? Fluorine or hydrogen chloride? Now pay attention, they have comparable molar mass. Why is that? So I can tell you that dispersion forces is the same. So now you're comparing what? You're comparing major intermolecular force. For fluorine molecule, it's London dispersion forces, it's not nonpolar. For hydrogen chloride, it's a polar molecule, it's dipole-dipole. Therefore, hydrogen chloride has a stronger intermolecular force and larger boiling point. So if you look at the boiling point of hydrogen chloride, it's negative 85 degrees Celsius, while for fluorine gas, it's negative 188 degrees Celsius. Xenon or argon, both of them are noble gases. Both of them are nonpolar interaction with other noble gases molecules. It's going to have to depend on London dispersion forces. Xenon is heavier, therefore more electrons, more London dispersion forces, and higher boiling point. If you look here, you will see that xenon definitely have a higher boiling point than argon. There are two other definitions that also reflection of intermolecular forces. The first definition is critical temperature. Critical temperature is the temperature above which the gas cannot liquefy no matter what pressure you apply. And a critical pressure is that amount of pressure needed to liquefy at the critical temperature. So at one temperature, there will be a temperature, and that temperature is normally very, very, very high. Above this temperature, no matter what pressure you do or you apply, you cannot bring the liquid to become, you cannot liquefy the gas anymore. No matter how much pressure you apply, the gas cannot get to be liquid or cannot be compressed to be a liquid. And the last time you can possibly liquefy gas is at the critical temperature. And at that critical temperature, above it, you can never liquefy, but at that critical temperature, you have to apply a critical pressure, which is the minimum pressure needed to liquefy the gas at the critical temperature, and that pressure is also very, very high. These two values depend on intermolecular forces. The stronger the intermolecular force, the higher the critical temperature and the higher the critical pressure. This table shows examples of different molecules with the critical pressure and temperature, and you can simply, if you start analyzing them, see that it's dependent on intermolecular force. Let's look at another change. What about solid to liquid? When I go from solid to liquid, I call this process melting or fusion. The opposite, liquid to solid, is what I call freezing. So the melting of a solid, or the freezing point of a liquid, which is the same temperature, by the way, is the temperature at which the solid and the liquid phase coexist in equilibrium. The normal melting point, when I say normal, it means I define the pressure to be 1 atmosphere. Okay, now let's look at what we call a heating curve. A heating curve is showing you here what happens as I add energy across the x-axis with time. So this here is the freezing point. Anything below, if this is the temperature, so the y-axis is temperature, anything below the freezing point will be solid. At the freezing point, from point A to point B, you're going to have solid and liquid coexisting in equilibrium. So if this is water, this here will be 0 degrees Celsius. And this will be all solid at 0. And as you add energy with time, that will convert it to all liquid excuse me, at 0. Then you keep adding energy to that liquid. It will go up in temperature till it reaches the boiling point. That will be 100 degrees Celsius for water. And this will be all liquid at 100. Then you start vaporization. In this area, liquid and vapor will coexist. And you will convert all your liquid at 100 to vapor at 100 at this point. When all is vapor, you add more heat, it will all become vapor, and it will start increasing in temperature. This is what we call the heating curve. The smaller area between A and B is a measure of heat of fusion. What do we need to convert all the solid to liquid at the freezing point? And between C and D, it's what we call the exchange of heat of vaporization, which is taking all your liquid at the boiling point to gas at the boiling point. It's always the case that heat of vaporization is larger in amount than heat of fusion. It takes more to vaporize than to melt. Let's look at the next one here, which is going from solid to gas. We call this sublimation, and the opposite will be deposition. And the molar heat of sublimation is the energy in kilojoule normally required to sublime a mole of a solid. Now, heat of sublimation will equal heat of fusion plus heat of vaporization. I mean, look at it here on the diagram. This is also Hess's law, by the way, right? This is heat of sublimation, which equals heat of fusion plus heat of vaporization. You add them up together. And that's as long as everything takes the changes at the same temperature. All right, so this is a problem that I want you to solve on your own. There's something we've gone through before in different chapters, I think in the thermodynamic chapter. I'm going to explain the problem to you, but I will make you and give you the opportunity to work on it on your own. Calculate the amount of energy released when 346 grams of steam at 182 degrees Celsius is converted to liquid at 0 degrees Celsius. So remember, this is the heating curve. And what you are required, this is the way you add heat. But they are asking you to go the opposite way. So I'm going to change the color. They want you to go from steam at 182 degrees Celsius all the way to liquid water at 0. So this is solid water at 0, and this is here liquid water at 0. So you're going to go from this point to this point. The first one, you're going to go from 180 to 100, and you're going to use, because you are having change of temperature, Q equals M times S times delta T. And you are given the specific heat of the steam right here, right? And remember that the final temperature in your case here is 100. Then you're going to go from this point to this point with this horizontal line, and this is heat of vaporization. But remember, you're actually doing condensation going this way. So if heat of vaporization was positive, the other one will be negative. Then you're going to take water from 100 to 0, and you're going to use again Q equals M times S times delta T. You have S for water, and this is final temperature is 0. And that the last amount is, they are all going to be negative because delta T for these two are negative. The final is lower than the initial. And for this one will also be negative because, as I explained, this value you have to convert the sign. You have a 3 segment. The answer will be adding those 3 segments to each other. Now we're going to look at the phase diagram. Phase diagram is a diagram that summarizes the conditions at which the substance exists as a solid, liquid, or a gas. So here is a phase diagram. On the y-axis, we always have pressure. On the x-axis, we have temperature. The first thing I want to bring to your attention on the phase diagram, something we call the triple point. Triple point, it's the only condition under which all 3 phases can be in equilibrium or coexist. For water, this happened to be if you have water at 0.01 degrees Celsius and 0.00603 atmosphere, then water will exist as gas, liquid, and solid. That's why you don't see it, because we don't have this condition at room temperature, right? You have to provide special conditions for that. Now, normally when we give you a phase diagram, we will give it to you this way, and you need to know where are the 3 phases. So pressure goes up here and temperature goes up here. So what phase this is how you will figure out the phases in case you cannot memorize it. What phase will dominate if I keep increasing the temperature and lower the pressure, which is here? That should be the gas. And what phase will dominate at low temperature and high pressure? That should be the solid, and therefore liquid will be in the middle. Now, you can always figure out, for example, what temperature will be boiling, the boiling point. You go to the atmosphere, and then you go to the line, which is C to A. What does that line? This is a line where I have the equilibrium between liquid and gas. This is where vaporization and condensation takes place. So right here, that dot here is where water boils. So if I go down onto the x-axis, I will find out the boiling point. What does that line here represent? This is the line where I have melting and freezing taking place. And that line here where I have sublimation and decomposition take place. So I can, for example, ask you, can sublimation ever take place above, let's wipe everything from the diagram and show you how to ask a question. So, can sublimation ever take place above 1 atmosphere? So you go to 1 atmosphere. I will take 1 atmosphere right here. And above 1 atmosphere, if you go above 1 atmosphere, right, what are the changes that are possible? You can have that kind of change between liquid and solid, and you can have a change between solid and gas, but there is no change between solid and gas, so therefore you cannot have sublimation. You can only have sublimation under that value, whatever that value is. This is where sublimation can take place. So I can look at this phase diagram and figure out what will happen if I cross at that temperature and at that pressure. What is the state? What are the physical changes that are going to happen? You can also see the critical temperature, this last point here. Now remember, higher than this temperature, it's all going to be yellow. Why? Yellow is a gas. Like no matter what pressure you apply, it will stay gas, and that's the definition of a critical temperature. Now, when we go and look at another picture here, this picture shows you what I was trying to explain, the different changes and the different processes at every line on the phase diagram. This is the phase diagram between water and any typical substance, and this is really important. Any typical substance will look like that. Here is carbon dioxide as an example. Only water has that phase diagram. So what's the difference between them? The difference really is in the slope of this line right here. All substances will have that slope except for water will have the slope going to the left. And the reason for it, it's because water is the only substance in which the solid can be less dense than the liquid. So the highest density can get when I apply the most pressure and on a substance. And when I go up in the pressure here, which is above 0, right, I cross the liquid and I don't cross the solid, right? Unlike the other substances here, if I go and I increase the pressure, then I am hitting, for sure, I will be hitting the solid, right? Because this is here is your temperature where you're gonna go up and increase the pressure, and the only thing you will get a solid. While for water here, as we have, if you guys remember the diagram we have seen earlier for the water, at 4 degrees Celsius, water has the highest density and it's a liquid state rather than a solid state. So the reason why water is different, because water is the only substance that the solid can be less dense than liquid. So remember that when you identify the phase diagram of any substance, remember to look at that and figure out what is the slope of this line, and you will know if we are looking at water or if we're looking at anything else, because anything else will look just like the carbon dioxide phase diagram. Water is the only one with that tilted slope to the left, because the liquid state will be the liquid state will be the most dense state at 4 degrees Celsius for water. That definitely does conclude this chapter. And again, just make sure that you are aware of the phase diagrams, you are aware of the slope that shows the difference between water and other substances. And I will see you in the next chapter talking about solids. Thank you and have a good day.